Okay, so this is a very quick going through the step module in Abacus, and this would probably be the last so-called lab or any more information on Abacus from my side, unless you have more questions that you're feel free to ask me, and maybe I can compile all the question in one Abacus video for your finals project. Um, so let's go and look at how we actually do the quasi-static analysis in Abacus. So this is one of the, I think, the first lab that we ever did. I have reloaded the file and I'm looking at my load step that I created. Okay, and I'm gonna right click on it and hit edit. And once I hit edit, since it's a static general, you can see the type of that step right away. It's a static general. We're gonna use it in a quasi-static form, which is again a very common way to do a finite element analysis. Okay, so unless you are working with a high strain or stress rate conditions or high loading rate conditions, which are very, very close to the minimum natural frequency um, calculated for your structure, you don't want to use the dynamic analysis just because it's very computationally expensive as compared to this quasi-static analysis. Okay, so when you open this edit step window, in the basic one you can either provide a description of your step if you want to, but the main thing I want to focus is the time period. Okay, you can, by default the time period is 1 second, but you can make it 10, 100, 200 seconds. um, the next tab is incrementation. Okay, so an incrementation, that is the size that you want to give for delta t, right? As we see in our analysis, um, delta t for a quasi-static condition will always add up to the final time, the total time duration. Okay, so for a given time period of 1 second, and if I keep my increment size to 0.1 second, um, there are three tabs for increment size too, so I can have my initial increment, maximum allowed increment will be the same as the maximum increment in any of these three windows, and the minimum increment, just in case the analysis does not converge. It can cut down the increment size, so cutting down the amount of force or amount of displacement in that given delta t, so that the converged solution can be calculated. Okay, now another thing, you can adjust. So now hopefully you're clear on how to adjust the increment size. I generally leave the initial and maximum increment sizes to be the same, um, because I can't have the maximum increment. um, I can't have maximum increment size that is smaller than the initial increment size. So by default, leave it at the same. Minimum, leave it as 1e minus 5 or even lower if for some reason your analysis doesn't converge. But for the cases that you'll be working with, you might be just fine using minimum increment size of default value here. Now, look at the maximum number of increments allowed. That is the number of increments which is equal to the total time duration, over here, time period, divided by the amount, the increment size. So in this case, number of increments I would need at least would be 10, um, but you can leave this number as high as possible, so that even if at for any time increment the solution doesn't converge and it cuts down the time increment into, for example, half, so let's say it goes down to 0.05, you still have enough number of increments allowed left in the analysis, so that analysis continues. Okay, so by default, for increment size of 0.1, I would need about 10 increments to finish this analysis, because 10 increments will lead to my final time duration to be 1 second, right? But what if I left this to be 5 increment, then analysis will only go up to those 5 increments and it fail after, it will cancel, abort the analysis after that. So make sure you have sufficient number of increments here so that your analysis runs without getting into this condition right here. Okay. All the other option, you want to leave it as a default. um, for example, you can change incrementation type from automatic to fixed. If you go for a fixed, then your increment size is one size only. So for example, for that given increment, if the solution did not converge, it doesn't have an option to cut down the increment size and try to run the convergence again. Okay, so I would leave it up to automatic, so that it can, at the end of the day, gives you a converged solution. So that is it for this, for to define the quasi-static analysis. Oh, one more thing, sorry. For this quasi-static analysis of, let's say, final time period to be 1, when you're looking at your boundary condition, um, for example, we have displace the right face here. Okay, so I'm gonna right click and edit on that, and I'm gonna see. So I have a -10 value of displacement. That -10 value is the total displacement by the end of the analysis. Okay, so try to think about, and per time increment now, if my time increment is 0.1 second, then per time increment I'll have a -1 a displacement in the y direction. Okay, so this displacement value that you prescribe here for your boundary condition is the total displacement during the analysis over the given analysis time. For example, 1 second, and you can give it 10 seconds, 50 seconds, so on and so forth. As far as your problem is not dynamic, does not come in a dynamic range, dynamic category. Okay, so these are the two main points to focus on for a quasi-static analysis. Do let me know if you have any more questions, and I can maybe create another video if you have very specific questions in Abaqus, and if that is something that you really needed clarified for your project. Okay, have a good one.